Hey guys, Professor Sweeting here. In this video we're going to continue our study of coloring problems by looking at the minimum coloring problem for edges. We will briefly discuss some differences between this problem and the vertex coloring problem, compute the edge chromatic number of some graph families, and look at problems which can be modeled by graphs and solved via edge coloring. So the edge coloring problem. This problem is the minimum coloring problem with respect to edges. So for this problem we're looking for an assignment of a color or label to each edge of a graph so that no two edges sharing a vertex have the same color and which uses the fewest number of colors to do so. Right? So this is an example or particular instance of that minimum coloring problem that we had talked about in terms of components in that introduction video. Right? So for that general minimum coloring problem, we were looking at some component within the graph, whether it be the edge, vertex, or face, and we were trying to assign to each of that component in the graph a color so that adjacent components had different colors, and the notion of adjacency varied for each particular instance. So in this case, the components are the edges of the graph, and adjacency between components, right, which are edges in this case, is when two edges share a common vertex. So I just want you guys to realize that this is just a particular instance of that general type of problem. So this minimum number of colors for a given graph has a special name. It's known as the edge chromatic number of that graph. So let's look at a few examples. So if I had a graph here with 3 vertices and 3 edges, we're going to, via a process of trial and error, find a minimum edge coloring of this graph. Okay? And, therefore determine the edge chromatic number as well of this graph. Okay, so we can start with this vertex here, and we know that all of the edges that touch this vertex have to have a different color because they would be considered adjacent, right? Because they share this vertex. That would be these two edges, so we can assign each of these edges a different color / label. So I'll be using both colors and labels, but I'll be saying color. So remember from the introduction video, this minimum coloring problem is essentially a labeling problem. So these colors are labels. So yeah, it's not necessarily about coloring things, but rather labeling things. But it's nicer when we use colors as the labels because it's a friendlier makes things friendlier, right? Okay, and more approachable. All right, so once we've done, so this was required, right, of these two edges because they share this vertex and are therefore considered adjacent, right? So the coloring isn't done yet because we still have one final edge that hasn't been assigned a color, all right? So in our process of trial and error, we're going to try and assign it a color that we previously used so we can make sure that we're using the minimum number of colors, right? But can we do that, right? So this edge, well, it shares this vertex with this edge that we colored green, gave this label A. So it can't have that same label / color, and it also shares a vertex with the edge that we colored pink and gave this label B, right? So it also can't be this color / have this label. So it needs to have a different color / label from the other two edges, and we assign it that. Okay. All right, and our coloring is complete. Okay, so through that process, we determined that this is the minimum number of colors needed, right? So therefore, the edge chromatic number of this graph is 3. Okay, let's look at a minimum edge coloring of another graph here. Okay, one with 6 vertices and 6 edges. Okay, so this is a cyclic graph, right? So we've seen this type of graph before. It belongs to a graph family called the cyclic graphs. Right? And what is the defining characteristic of graphs in this family? Well, these are graphs that are connected and whose vertices each have valence 2. Right? So this is the property, right? Or these are the properties that define graphs in this family. We can see that this is a connected graph. We can get from every vertex to any other vertex via path in the graph, and each vertex has valence 2. Okay? So we'll see later, as we had seen in the first video, that this is one of the families for which we know for every graph in that family the edge chromatic number, or the answer to this coloring problem. Okay, but let's just try and figure out via a process of trial and error what the minimum, or find a minimum edge coloring of this graph and find what its edge chromatic number is. Okay, so we can start as we had in the first example and fix a vertex and look at the edges that touch it, right, which are these two. We know that they're adjacent because they share this vertex, and so they have to be a different color from one another. Okay. Alright, and in our process of trial and error, since we're trying to find a minimum edge coloring, we are going to try and reuse the colors that we already used for coloring the remaining edges. So let's go around here counterclockwise. So we can reuse this green. So this may not always work out. Alright, and then we can reuse pink, because if we assign this pink, or give it the label B, then it has a different color / label from its adjacent edge, so it's adjacent to these two, right? And then assigning that color means we have to assign this edge, which is adjacent to that edge, a different color, but we could just reuse one of the colors that we've already assigned, and do the same thing for the last edge here. Right, and there you have it. So we've colored every edge of this graph such that all edges sharing a vertex have a different color, and we did so with the fewest number of colors possible. How do we know this is the fewest? Well, we certainly can't do it with one color, so therefore the edge chromatic number of this graph is 2. So we'll see later how to determine this for all graphs that belong to this family, not just for this particular instance of a cyclic graph. Alright. So while the edge coloring problem and the vertex coloring problem are very similar in statement, they are completely different in terms of analysis. For one, while it was very difficult to determine the chromatic number of an arbitrary graph, so the only estimate, so remember, chromatic number is the minimum number of colors needed to color the vertices of a graph so that adjacent vertices, meaning vertices connected by an edge, have different colors, right? The only estimate we'd have is that this chromatic number is less than the total number of vertices, which would correspond to giving every vertex a different color. However, the case for finding the edge chromatic number is much easier. Right away, we have a sensible lower estimate by simply looking at the valences of its vertices. By a simple argument, we can see that a graph's edge chromatic number has to be at least as large as the largest valence of its vertices, called its maximum degree. So the maximum degree of a graph is the largest valence of its vertices. Okay, so let's see what we mean here by that. So how do we have this good estimate? Right, so say we had a very complicated graph here, well, at least relative compared to the two that we've considered so far, something along the lines of this. And we were trying to figure out what the edge chromatic number was of this graph, right? Or find an edge coloring, and we wanted to know how many colors we would need to use at least, right? Well, we can look at the vertex with the largest valence, right? In this case, which is this vertex, right? right, which has a valence of 5. And that gives us a lower bound for the edge chromatic number of the graph, because all of the edges touching this vertex, of which there are 5, because this vertex has valence 5, that's the definition of valence, will need to have a different color, right? So each of these edges touching this vertex need to have a different color / label. Hopefully that shows up. So kind of running out of colors here. Let's see. Maybe this might show up. So this is a different color blue here. It's like a lighter blue. Okay, and then let's give labels here. A, B, C, D, E. Right, so we know that the edge chromatic number has to be at least 5, because we have a vertex with valence 5, which means 5 edges meeting at one vertex, meaning 5 adjacent edges. So each of these needs to have a different color. Okay, so we didn't really have an analog to that in the case of the vertex coloring problem. Okay, all right. So in fact, this estimate is very good. So a special theorem called Vizing's theorem states that for the graphs we've been studying, called simple graphs, so every graph that we've looked at in this class is a simple graph, right? So their edge chromatic number is either equal to or one more than their maximum degree. Okay, so that means that for any given graph, the edge chromatic number will be either equal to the largest valence of a vertex in the graph or one more than that value. So we can see that holding, I mean, we didn't find out what the edge chromatic number in this case is. It seems like it would be equal to 5. So we can reuse these colors here. Right. Colors / labels. Okay. So in this case, I can actually reuse green as well. Okay. C, B, B. Okay, so in this case, the maximum degree of the graph is 5, and the edge chromatic number is 5. Or it's one more than the maximum degree. So that's the case in this graph here. So the maximum degree of this graph, which is the largest valence of a vertex in this graph, is 2, but the edge chromatic number is 3. So Vizing's theorem says that for any graph, any simple graph, this is the case. So a simple graph is just one that's not directed and it doesn't have loops, right? Or like duplicate edges. So that's a simple graph. I believe simple graphs can't have duplicate edges. So no loops, no duplicate edges, meaning the same two edges connecting the same two vertices. So for all such graphs like that, which are essentially all the graphs that we've looked at so far, the edge chromatic number of a graph is either equal to the maximum degree, as it is here and here, or it's one more than the maximum degree, as it is in this graph. So this is a far more regulated situation than what we had with vertex coloring. There are literally only two possibilities for the edge chromatic number with respect to the maximum degree of the graph. Alright, so it's a far more regulated situation. Now, despite there being only two possibilities for the edge chromatic number of a graph, it can still take some effort to compute this value, so determine which of the two possible values it is. Moreover, just knowing the edge chromatic number of a graph doesn't actually help us find a specific coloring using those colors. A good analogy here would be the problem of finding an Euler circuit. Just knowing a graph possesses an Euler circuit doesn't actually help us find one. So we can look at these graphs that we've considered. We know this graph requires has an edge chromatic number of either 5 or 6 because its maximum degree is 5, right? But actually taking those 5 or 6 colors and coloring in the edges still requires some effort. You can, as you're coloring, maybe work yourself into a corner. It is a difficult process, just as it was finding an Euler circuit in a graph that we knew had an Euler circuit, right, by the Euler circuit theorem. Okay. However, just as what was the case for the vertex coloring problem, there are certain graph families for which we do know how to solve the aforementioned problems. Meaning, for these graph families, we can know exactly what the edge chromatic number is for a graph in that family, and in some cases even have an algorithm for finding a coloring using those colors, right? A minimum coloring using that number of colors of any instance of a graph from that family. All right, so for example, the 3 graph families introduced in the last video: bipartite, complete, and cyclic graphs. So let's take a look at these as well as the family of tree graphs. Okay. So let's look at cyclic graphs. All right, so cyclic. So these are things that they're connected graphs. I put the definition on the last page. So if you forgot already, you could just refer, back up in the video a bit. So cyclic graphs are just connected graphs where the valence of every vertex is 2. All right, so these are all instances of cyclic graphs. So for graphs in this family, we knew what the chromatic number was. It was either 2 if the graph had an even number of vertices, or 3 if the graph had an odd number of vertices. Well, for the edge chromatic number, it's the exact same thing, right? And there's even an algorithm for finding such a coloring. So, as we saw, we checked out this graph already with 3 vertices and 3 edges. We had that for this graph, the edge chromatic number was 3. Okay. Let's give our colors / labels there. And we also looked at the edge chromatic number for this cyclic graph. And it was 2, right? And we can also look at the edge chromatic number for this member of that family, of the cyclic graph family, right? And this one will happen to be 3 as well. Okay? Oh, I should probably give these labels as well. Okay, so in general, right, we're not going to provide a rigorous argument for this, but the edge chromatic number for a cyclic graph is either 2 if even number of vertices, or 3 if odd. Okay? Alright, so that handles that graph family. And then we had bipartite graphs, which are graphs that consist of 2 columns of vertices, where a left column and a right column, where all of the vertices in the left column are connected to the right column, and vice versa. All vertices in the right column are connected to vertices in the left column, but there are no connections among vertices in the same column. Right? So here's an example of a bipartite graph. Another example of a bipartite graph would be this right here. Alright, so the number of vertices in each column can differ. Okay, so what is the edge chromatic number of elements in this graph family? Well, let's look at a simple example and see if we can reason something here, right? Okay, so we can start with this vertex, right? So we can actually just look at the graph as a whole, and we can use that estimate. So we know that the maximum degree, which is the largest valence of a vertex in the graph, is 2 here, right? So this graph either has an edge chromatic number of 2 or 3, okay? So let's try and start with 2 colors and see if we can find a minimum edge color. So we can color these 2 edges because they share a vertex different colors, so we have to, right? And then let's try to reuse the colors we already used. All right. Technically, these edges are crossing one another, but they're not adjacent because they're not touching at a vertex. That's the definition of adjacency. That's what's not allowed, right? For adjacent edges to have the same color. So, looks like we were able to find an edge coloring here, and obviously it's minimum, right? So the edge chromatic number here, right? This is how I'm abbreviating edge chromatic number, is 2, right? Let's see what's the case for this bipartite graph here. Well, we can connect this one, where these have to be different colors. Okay, we know it's at least going to be 3. Okay? So the edge chromatic number of this graph is either 3 or 4 because the maximum degree, which is the largest valence of a vertex in the graph, is 3. Right? So we look, at one of these vertices in the right column and we see that they have a valence of 3. So we know it's either 3 or 4, the edge chromatic number of this graph. Okay? Alright, so we started with this vertex, but it might have been easier to start with one of these. But in any case, so we're going to try to reuse as many colors as possible. I think it's safe to color these two this color. I think I may have put myself, that might not be the correct coloring here, because that would require this to be this color, and this would have to be a different color from both. I should be giving these labels as well. A, B, B, C for that color for this edge, and then this would have to be a different color from both. So this is not optimal, right? Because as we'll see, we'll find a different edge coloring. So this is not a minimum edge coloring of this graph, right? But we'll see that for bipartite graphs, edge chromatic number is either maximum degree. Oh, excuse me. I just lost my train. So it is actually the edge chromatic number of a bipartite graph is its maximum degree. So this is just an illustration. So these kind of arguments are a bit beyond the scope of the class, right, to provide why that's the case. So I'm just looking at trial and error at a few examples, but not providing a rigorous proof and trying to establish this conclusion. So alright, so this is not, as you can see, it can be a difficult process, or it can be a tricky process, finding an optimal edge coloring, even though we know how many colors we need to use. It's either one of 2 things, based on the maximum degree of the graph. Okay, so let's try something else here. Let's try, alright, starting with one of these vertices. So we can do this color, this color, and this color. Okay? So we're still going by trial and error. And let's see. So what restrictions do we have? So this edge, I should be labeling these A, C, B. Okay, so this edge right here, from the first element of this column to the second element of this column, cannot be, the only restriction on this is that it can't be green or have the label A, right? So, yeah. So we can try and reuse one of the previous two colors that we've used. Okay, so where we made a mistake here was using, alright, so maybe it's not best to start with that edge. Let's just try something different where in this first example, well, I think I'm not going to talk through this, so I'm just going to try and do it first and then explain. Okay, so let's see. Trying to use 3 colors here. So what if I made this green? Then that necessitates this to be yellow. And then lastly, we can use pink here. Okay, so that works. Okay, I just did that from guessing. This is a process of trial and error. But there is a general algorithm that can be used to find, sorry if my labels are getting a bit cramped. So A, C, C, B, B. Okay, so there is a general algorithm for bipartite graphs that gives us a minimum edge coloring for such a graph. Okay, but again, so for bipartite graphs, the edge chromatic number is the maximum degree of that graph. Okay, so this video is getting kind of long. I think in the next one, I'm going to continue with complete graphs, and we're going to look at their edge chromatic number, and we're going to talk about trees as well, and then look at an example of a problem that can be modeled by graphs and solved via edge color.